So hello and welcome to this technical introduction to Vivado HLS. If we look at our valve slides, we can see what Vivado HLS adds to this. In principle, the accelerated design productivity. With better designs, Vivado HLS can contribute to all of the valves. It can reduce power, it can reduce bill of materials, it can reduce system performance, but its key differentiator is in accelerating design productivity. The things we'll review today are to show you how Vivado can, by using C and C++, create a more efficient specification. We can do design-based, directive-based design exploration, and with comprehensive integration with the entire Vivado design suite. So to give you an overview of Vivado HLS, we can look at this diagram. So as you'll see there on the left-hand side, as most of you probably know, Vivado HLS takes C, C++ or System C, and then synthesizes it down to Verilog or VHDL, where we can integrate that system, that IP into the system. In the center there, you can see this is more of a textual transformation to gates and registers. On the right-hand side, we can see an overview that we take an algorithm, we can do some microarchitecture exploration, and finalize with an RTL implementation. Okay. Here we can see a different perspective of how Vivado HLS can be used. Typically, a requirement is taken to a software domain and a hardware domain. Vivado HLS allows us to take some of that software and create accelerators. This is a very important use for Vivado HLS, especially with the Zyng device, and it's something we'll see more of in today's presentation. And finally, Vivado HLS is available today for all customers. It synthesizes C, C++, and System C. It has been well adopted among Xilinx users and is clearly out there in the marketplace. Okay. Here's a more in-depth or system view of Vivado HLS. So again, we take C, C++, or System C through to Verilog or VHDL. Now the other thing you'll notice in this diagram here is that Vivado HLS, the C, C++, is also including C libraries, either math.h, some video, or some DSP libraries which are coming later this year, the second half of 2013. And you'll see there the sign for OpenCV. We'll discuss this more in this presentation, but Vivado HLS does use a number of C libraries to improve the performance of the designs. When we take the output of Vivado HLS, it can be exported into the IP catalog and throughout the rest of the Xilinx Vivado design suite. So it can be imported as an RTL block into Vivado RTL. It can be used in Vivado IP Integrator, and it can be used as a single block in System Generator for DSP. So the output of Vivado HLS can be added to the IP catalog and used throughout the entire Xilinx ecosystem. So let's now have an overview of C synthesis. So here we have an example of some C code. If you look at the C code, you'll see it's basically an FIR filter. It comes down, it sets an accumulator to 0, and it then goes around a loop, okay, from 3 down to 0. It's a small example. If I equals 0, it starts at 3, so we don't do that to begin with. We go to the else branch. We'll essentially shift items along a shift register, and we'll multiply the shift register with the coefficients and accumulate. And then finally, when I equals 0, we'll accumulate that once more, and we'll shift X, the new input, into the front of the shift register. And finally, we'll come out of the loop, and we'll assign the accumulator to the output port Y. So a small standard FIR filter. Now if we look at this filter, we'll see that it does have a number of loops. Okay. Here we can see at the top we have the start of the function and the end of the function, which itself is an infinite loop. And we have the start of a for loop and the end of a for loop. Vivado HLS can extract this information, and from this it can construct a state machine for this design. So that if you were building this as an RTL engineer, you would build a state machine where it comes in, you do a basic operation, you then go into the for loop, you go around multiple times, come out the for loop, write the result, and then go back to the start of the design. So as you can see, if you look at this C code, you can see how Vivado HLS can extract the control logic. Okay. Now, if we take that same C code, it does also contain a lot of operators. So given that Vivado HLS has already extracted this control states, these operators can be placed into the control to create the final design. So this, I wouldn't say the final design, rather this is the initial design. Okay, and from this, Vivado HLS using directives can create many more different designs, as we'll see later in this presentation. So So for example, that for loop could be unrolled. We could do it multiple times. We could do everything in parallel. But this gives you an idea of how high-level synthesis works, and it's not in fact any sort of black magic. It's a deterministic process, and by looking at the loops in the C code, we can see how things can be synthesized. So again, as an overview in this C code, let's have a look at its primary aspects. All C code contains functions. As we'll see, these functions represent the hierarchy in the design. Okay. The top-level arguments to functions, these will become the I/O ports in the RTL design. All C code is full of types. These types influence the area and the performance because they define the size of the operations. All C code, or most of it, typically contains loops, and we'll have a look at how loops are synthesized and what options you have when synthesizing these. Again, arrays are very common. We'll look at how arrays are synthesized and how they can impact performance. And finally, the operators. Like the data types, these influence the area and the performance of the device. So the first thing to do is let's have a look at how all of these are synthesized by default. Okay. So if we look at functions, on the left-hand side here, we have some source code where you see a top-level function at the bottom has functions A, C, and D within it. Functions C and D both have a function B within those. When this is synthesized into hardware, we end up with a hierarchy. We have a top level called foo top. Inside that, there are 3 blocks, A, C, and D. And within C and D, there's a block called B. So you can see that the functions in the C code synthesize directly to the RTL hierarchy. Now, these blocks can also be shared, provided they're not being used at the same time. Okay? They can also be inlined, and like RTL, you can dissolve that hierarchy automatically. The advantages, like RTL, the advantages of dissolving the hierarchy are that we can do more optimization. The disadvantages are we then have more operators to work with, and so runtime may slow down. Okay? But that's essentially how functions are synthesized. The other thing we looked at are the arguments to the top-level functions. In this example, we can see there are 2 inputs, in-picks, out-picks, and two other inputs, rows and columns. Okay? When this is synthesized, it's synthesized into the block below. So first of all, we would add a clock and reset port. Now, in addition to the standard inputs, Vivado HLS optionally adds, and by default adds, some block-level control signals, such as a start, a done, and idle. And this allows us to tell when this block can start and when it's done. And from this done signal, for example, we could generate an interrupt. Okay? The ports are then synthesized. In this case, we could decide that we're not going to have any I/O protocol on these ports. And then the other 2 ports, in and out picks, can be synthesized, for example, into a FIFO port and an output FIFO port. In addition to these ports, we can also add bus-level interfaces. So, for example, when we export the RTL, we could decide that this input FIFO port will in fact become an AXI stream port, and the output FIFO could become an output AXI stream port. We can also create an AXI Lite interface, and because we can create an AXI Lite interface, we can actually group many, many different ports together into an interface that can actually be addressed via the CPU. So you can see that we can actually build up a fairly complex I/O protocol controls and connect this block up into a wider system. The other thing that's common in C design are loops. So if we look at this example here, we have a small loop. Okay, we simply iterate around from 3 down to 0, and we sum AI plus B. When Vivado HLS creates this hardware, it will create a single body for the loop, a single block of hardware for the loop body. So if we look at the diagram on the right-hand side there, you would basically see an accumulator. And for each iteration of that loop, we would go around and execute the same body of hardware. So here you simply see an adder, and we go around and we accumulate it. However, Vivado HLS allows you to actually unroll these loops. So you can look at the example on the bottom. We could decide that rather than take 4 clock cycles to do all the additions, we could just unroll that loop and do all the additions in a single clock cycle. Okay. Now, if in the case where we could not perform 4 additions in a single clock cycle, Vivado HLS would automatically add an adder in there to split up. So we may see 1 adder, a second adder, then a register, and then 2 more adders before we see the final result. Okay. So you can see that we can actually automatically unroll these loops, and we can partially unroll them. So we can unroll them by any factor. We can unroll them by 2, unroll them by 3, etc., etc., to get the most optimal implementation. Arrays, again, are another common feature of C code. Now, an array in C code, if we look at the left-hand side here, is a collection of elements accessed via an index, okay? And you can see that in the center. So we have a collection of elements all grouped together from 0 to n-1. That is actually the same thing in RTL as a RAM. It's a collection of elements only accessed via an address port, okay? And so arrays will synthesize by default into RAMs. They could be synthesized into block RAMs or LUT RAMs, single port RAMs, dual port RAMs. Any resource on the memory device, an array can be targeted to, okay? In addition to that, arrays can actually be merged with other arrays. So if the user has a design with lots of small arrays, you have many arrays using up only 10 elements. Each one of them would use up its own BRAM. You could actually merge all these into a single BRAM, okay? So the user doesn't have to change the C code. You could actually just merge all these together. More commonly, arrays can also be partitioned so that when you have a large array and you're trying to access multiple, when you have a large array, it synthesizes into a large RAM. When you're trying to access multiple elements of that RAM, there may be a bottleneck. Even with a dual port RAM, you only get 2 ports. Vivado HLS allows these arrays or RAMs now to be partitioned, okay, via directive. And so we could take these larger RAMs and automatically partition them into smaller RAMs, okay? And we can also completely partition them into registers, okay? The whole concept here is that the C code should remain as it was written, okay? And then we have directives, or the tool has directives, to be able to split these RAMs or merge these RAMs to create the most optimum design, okay? The last thing to talk about here, and maybe one of the most important, are the operators. So as we mentioned earlier, from any C code, we're going to generate a number of operations, a read on port X, a read on the coefficient port, greater than, multiplications, additions, etc. So each of these options, each of these operators will be defined by a standard C type. And so Vivado HLS supports all the standard C types. There's long, which means it's a 64-bit operation, short, which means it's a 16-bit operation, integer, char, etc. Vivado HLS also supports floats and doubles. For floats and doubles, all basic arithmetic is supported by the Xilinx IP cores for floats and doubles. For math operators, there's a library that Vivado HLS supports. It supports, for example, sine, cos, arctan, etc. Not every member of the math.h library is supported, and those that are supported are listed in the Vivado HLS user guide. But all the most common that cover maybe 80-90% of all cases are used. So what this means is that when the users synthesize this code, the size of the operators will be determined by the data type. So for example, if the user calls the data type int, it will result in the 32-bit operation. So int times int is a 32-bit multiplier. The problem with C is that all these data types exist on boundaries, 8-bit boundaries. If we look at this, we can see 8-bit, 16-bit, 32-bit, 64-bit. This is not the most optimum for producing high-quality hardware. And so Vivado HLS provides a number of arbitrary precision data types. So here you see we have arbitrary precision data types for C, C++, and C++ and System C, okay? What an arbitrary precision data type is a data type that can represent any value. So for example, if we look at the first line there, C, from 1 to 1024, and C++, 1 to 1024, okay? So this allows us to create data bits of any size, for example, 17-bit, 47-bit, 12-bit. And this is one of the greatest advantages of using Vivado HLS. So for example, if the user was designing a FIR filter, and it was very important that the signal-to-noise ratio, two things. It's very important that the multiplications were only 12-bit, so that everything could be accumulated into a DSP48. The user could use these exact sizes in the C code, and more importantly, the user could then simulate this C code to confirm that they have all the correct values. They could double-check their signal-to-noise ratio, and they can do all their analysis in C, which runs much, much faster than RTL Simulation. Once they're happy with that, they can simply just synthesize that and get the exact same behavior at the RT level. Okay. So that's an overview of how the operations work. When it comes to the actual C itself, or how the main operators in C are synthesized, when it comes to C itself, the vast majority of C and C++ is supported. The key for knowing what is synthesizable and what is not is basically if it's statically defined at compile time, we'll be able to synthesize. If it's not defined until runtime, it won't be able to synthesize. So certain things must be changed or cannot be synthesized. For example, dynamic memory allocation. For dynamic memory allocation, the size is indeterminate. If we're going to synthesize the hardware, we have to know that it will be, for example, a 9 KB RAM. We can't build hardware where it may be 9 KB RAM, or it may be 9 bytes, or it may be 9 gig. It has to be defined at synthesis time, okay? And there are many examples in the coding style guide of how you could actually change this. The other thing that cannot be synthesized are system calls, so accesses to the disk or features of the operating system. You know, for example, to ask what is the date or what is the time, or to save things to a file. Things can be saved, and CPUs can be interrogated to find things like date, but everything has to be passed out through the I/O or the top level function arguments. That means they will become RTL I/O ports, and from there they can access the rest of the system. So you can actually save things out to memory that's outside. You can actually create ports that can be interrogated or get data from a CPU. You just can't use system calls within the C code to do this, because the operating system won't be there after synthesis. So most things can be synthesized, a few things cannot, okay? Now, certain things you may want to change, or the user may want to change. You know, when users write code for a CPU, and when they care about performance, or if they write it for a DSP or for a GPU, and they care about performance, they will actually modify that code in order to improve the performance. It's no different from an FPGA, okay? So there are cases where you may want to get better performance for an FPGA. Go ahead and modify the code, as it's no different from using a CPU, a DSP, or any other compile target. Okay. In summary, C code is a concise way to efficiently specify algorithms. It executes incredibly quickly. C code maps intuitively to hardware. The top level function arguments, they become I/O ports. Each function becomes a block in the RTL. Arrays are implemented as memories, and if the arrays exist on the top level function, they become memory ports. And loops mean execute the same hardware multiple times, but we have directives where we could actually unroll those loops and make everything happen in parallel. Changes to the C code. Great changes are not required. Some changes may help performance, okay? If performance matters, remember that people change code for GPUs, CPUs, and DSPs. It's no difference for for FPGAs, okay? So now, that's an overview of the C code and synthesis. Let's have a quick look into design optimization. First, we'll look at the most common optimizations, and then we'll look at an example, okay, of where you would change the C code. So here's probably the most common optimization that's done using Vivado HLS, and that is pipelining. If we look at this example code in the center of the screen, we're using some generic code here that does a read, a compute, and a write operation. And this loop is executed twice. Okay, if we look at the left-hand side, we can see how this would execute in hardware. We would do the read, compute, and write, and then we would do the read, the compute, and the write. Remember, in a loop, we create one body of hardware, and then we execute it multiple times. So it's executed in series, okay, or sequentially. The other thing we can see from this slide is the terminology that Vivado HLS uses. The interval is the number of cycles between when we can start new inputs. So in this case, it's 3 clock cycles. It takes us 3 clock cycles to finish, and then we can start doing the next set of operations, okay? The latency is the number of clock cycles it takes us to create an output. So you can see in this example, it takes 3 clock cycles before we can do the write operation. And therefore, it takes 6 clock cycles to execute all iterations of this loop, okay? So the most common thing people will do with this design is to have Vivado HLS automatically pipeline the RTL, okay? In this case, we simply add a directive, and Vivado HLS will create the RTL that behaves as shown in the right-hand side. Here, the latency is still 3 clock cycles, as we can see in the bottom, but the interval is now 1. So while we're doing a read, a compute, and a write, while we're doing that compute, the read port is not doing anything, so we could actually re-execute the next transaction, okay? And in this manner, we can get much higher performance out of the design. If you'll notice now, the loop latency is only 4 cycles. In a non-pipeline design, the latency of the total loop is typically interval times latency. In a pipeline design, is interval plus latency. And so you can see if the entire design was 1920 by 1080 iterations of that loop, it would be a large saving in latency and a large increase in performance. Here we're showing an example of a loop. Functions can also be pipelined in this exact same manner. Okay. The other more common optimization that's performed is to then do task level parallelism. So look at this example code here. Here we have 2 functions. There could also be 2 loops. One's called sepia, one's called sobel. Okay. So by default, these again at the loop level and the function level, these would execute in series. We would execute the first one, finish all the values, and then start to execute the second one. Dataflow optimization is a way of doing pipelining, but at a function or loop level. So for example, what we could do with Dataflow pipelining, if we look at the second bullet, is as we're executing the first filter, the sepia filter, as soon as data values become ready, the next filter would start to consume them. So again, it's like we're pipelining, but at the level of functions or loops. Okay, and this gives us much higher performance. In order to create this level of pipelining, Vivado HLS automatically creates memory channels between the functions or the loops. So as we can see in the bottom here, the default memory channel is a ping pong buffer. This is the default because it's the safest. No data can be lost. In most designs, this can actually be a FIFO as well as a RAM. And in most designs, when you have an interval of 1 and you're sending 1 sample each clock cycle, this RAM can typically be reduced to a 1 deep, okay? And so it doesn't really add much to the performance. So that's an idea of the 2 most common optimizations that can be performed by Vivado HLS. And this can be done without changing the C code by simply adding a few directives. The examples I've shown here have an interval of 1 where we're doing 1 sample every clock cycle. The interval could be changed to be 5, to be 10, to be whatever is the most optimal for the design. Okay? So the examples here are, you simply change a few directives and you get better code. Okay? The other type of optimization we can perform is by modifying the code. Okay? Now in this example, we're going to take a function that is initially designed to only operate in software, and we're going to take out one part of it and synthesize that into hardware and create an accelerator in the FPGA. Okay? This is very common with video algorithms. The algorithm we're going to use today uses OpenCV functions. OpenCV is an open source organization for computer vision. www.opencv.org. It provides over 2,500 functions for software engineers to use who are working on vision algorithms. Okay? Because they're all there, many software engineers use them. FPGAs are an ideal source for accelerating video, especially video that does lots of pixel level operations. People will try and do this in the CPU, or they even try to do it on a DSP. They typically never get it to run real time in HD, 1920, 1080 format. Okay. FPGAs are ideal for this, and this Vivado HLS can synthesize this code into the FPGA. Okay. Vivado HLS existing code, however, will typically result in low performance hardware. Okay. However, what we'll see, and I'll show you how this is done, Vivado HLS provides a video library, and Vivado HLS libraries ensure we actually get high performance hardware from this design. Okay. The best way to see this is to look at an example. So here on the left-hand side, we have a standard software design. The user will read an image using OpenCV. They'll use a chain of these OpenCV functions which are available for free, and they'll write the image out. Okay. Now our challenge is that on the right-hand side, we want to take this and implement it on a Zyng processor or a Zyng device. Okay. On the Zyng device there, we have the processing system on the ARM core in the corner, and then we have the FPGA fabric shown in yellow. Okay. So the first thing we do is we'd actually leave these blocks as they are. You know, these blocks we're going to continue to run on the ARM processor. Okay, these don't have to be accelerated. They're typically frame level optimizations. The OpenCV functions that perform pixel level optimizations, those we're going to create into a synthesizable block. These are going to be synthesized and executed inside the FPGA fabric. Okay. Now, in order to go from the OpenCV image to the synthesizable design, we need to change the format. And so within the C code, we'll take this OpenCV format and we'll convert it to our own AXI video format. Within the design, we'll then change that AXI video format into the matrix format that's used by the Vivado libraries. Okay. Similarly on the output, we'll convert from the matrix format to AXI and then from AXI format to OpenCV. And the whole reason for this is to enable us to have AXI interfaces on the ports of this synthesizable block, because this will give us A, a high performance interface, and B, allow us to easily connect up within everything else in the Vivado environment. Okay? So that's an overview of what we're going to achieve here. So let's look at a more detailed example. So here we have the existing software code. Okay? This is what an typical OpenCV design would look like in software. We would read the image in OpenCV format. There would be a list of OpenCV functions, for example, perform a Sobel operation, perform a scale operation, perform an erode and dilate operations. These functions are available from the OpenCV library and allow people to quickly do complex imaging tasks. And then finally, you would save the image. Okay? So let's look at how we would synthesize this or create a hardware accelerator. Okay? So the first thing we need is that Vivado HLS, there must be a single top-level function for synthesis. Okay? There must be one function, and we're going to synthesize everything below that. So we would capture a single top-level function. Now, if you've noticed in this, we've called the input data source underscore AXI and destination underscore AXI. Okay? So we're going to use AXI interfaces on this design. And let's see how we would add that. So in the software, the first thing we would do is we would just define a data type, and we'll call it AXI stream. Okay? In software, it's just another data type. It could just be, an int or a stream, or it could be a struct. For example, we can make it very similar to the AXI stream. It could have a T data, a T last, a T keep, etc. And the way we define this is to use the Vivado HLS libraries. We don't have to define it ourselves. We just have to include these libraries, and we can go define these streams. Okay? So once we've defined this, everything within this software code is ready to create AXI data types. Okay? The next thing we would do is transform that data. So we would add these two transformation functions. So here we would go from the standard OpenCV image to our AXI data type, and then on the other side of the function from our AXI data type back to the OpenCV image, OpenCV format. Okay? And that's basically it. That's all we need to do in the software code. Okay? So we're done here, and now we can go on to the part that's to be synthesized. Okay? So for the block for hardware acceleration, remember we have these AXI interfaces that we've added, so we should include the Vivado HLS library so that these interfaces can be defined. The next thing we would do is then create I/O ports, and we would use directives to do that. Now, rather than squeeze everything into the screen, let's look in more detail at how these are done. So one by one, here are the directives. Now, the other thing I'll notice here, as you'll notice in the top right-hand corner there, directives can either be tickle commands or they can be pragmas embedded into the C code. Okay? So in this example, I'm using pragmas that are embedded into the C code. Okay? But I'm just going to walk through them one by one. And so the first thing, we have our two inputs in this first bullet, input and output. And here we can actually say that input and output variables will be implemented using an AXI stream interface. And we're going to call them input stream and output stream. Okay? And that's all that's required, a simple directive, and AXI interfaces will be generated for this function after synthesis. The next ports we wish to deal with is we've added some rows and column ports. Okay? Now by default, these will get an I/O protocol. Okay? Now for rows and columns, they're not going to change during operation, so we don't need an I/O protocol. So if we give them the interface AP stable, we're basically telling Vivado HLS, just allow these ports to fan out. We don't need them to change. We don't need them to be registered. And finally, down the bottom, you'll see that As I mentioned earlier, Vivado HLS by default creates these block level control signals, start, done, etc. Okay? These are actually very useful when we're building designs based on AXI, because we can now group these into an AXI Lite interface. Okay? And the advantage of this is that these start and done control signals can now be accessed from the CPU. The CPU can control when this block starts, and then a done signal is used to generate an interrupt which the CPU can read. Okay? So these can be simply grouped into an AXI Lite interface by telling them that we're going to add it to an AXI slave. Now, because it's an AXI slave, we can add more than one port. And so what we can also do here is we can add the rows and columns also to this AXI Lite slave. Okay? Now, quite a few new directives there, but I think you get the point that by simply adding directives, we can create I/O ports. To see this in a bit more diagram sense or graphical sense, our C ports become an interface that looks like this. We have a control bus that groups all of the control ports, the rows and the columns that can be accessed by CPU. And the input and the output simply become AXI streams that are connected up. Okay? So if we go back to our C function, the next thing we have to do is create the OpenCV functions. Vivado HLS provides a series of functions in the library which are drop-in replacements for the OpenCV functions in the software. Okay. The difference with these is you'll see that these use fixed-sized inputs and outputs. For example, you can see there's an array going into the Sobel and arrays coming out rather than just arbitrary-sized C constructs. But they are basically drop-in replacements. If we go back and look at the C code for these earlier in the presentation, you'll see that they're virtually the same, just subtly different format. These functions are all provided in the Vivado HLS library. Again, all the functions provided are listed in the user guide. But all we have to do here is include this HLS video.library, and we can then go ahead and use these OpenCV functions in our synthesizable code. The advantage of using the synthesizable video library functions is that we're now guaranteed to get high performance hardware. Okay. The last thing we need to do here is change the formats. Okay, we're coming in on AXI format, but the libraries created in the Vivado video library use matrix format. Okay, so what we're going to do is we simply create a transformation from AXI video to matrix format. And again, these transformation functions are provided in the video libraries. There's nothing the user has to do. So you can see that by simply adding a few library function calls, you're able to come in on AXI and use these high performance OpenCV functions. That's the code basically written. The last thing we have to do before synthesis is we'd like to go and optimize this. So we can add a Dataflow optimization. Now, as I mentioned earlier, and we saw, Dataflow will actually essentially pipeline all of these functions at the function level, so that, well, before Sobel completes, it will start sending data to sub S. Before sub S completes, it will start sending data to scale, and we'll actually start to get a pretty high performance out of this entire chain. And that's basically what it takes in order to make a high performance accelerator part. Now, we'd like to talk about design integration. Okay, and this is the last part. We can show you how Vivado HLS helps you get your design that we've just created into a design on the device. So the first thing that Vivado HLS provides in its environment is a C compiler. Validating the C algorithm is one of the most important things the user can do, and it's also one of the greatest benefits of moving to high-level synthesis. The example we'll show here on the screen, a frame of video is processed in less than 15 seconds when you run it in C. If you run the RTL simulation for the same frame of video, it takes about 10 hours, and that's 10 hours in one of the big Linux boxes here that we have at Xilinx. Executing and refining your algorithm at the C is the greatest benefit of high-level synthesis. It's not so much the tool itself, it's the fact that you can develop your C algorithms and run with C simulation speeds. Seconds versus hours. There is a huge advantage to using C simulation to develop your algorithm. And because Vivado provides arbitrary precision types, users can then use the exact same bit width that they expect in the RTL in the C code, simulate it, and make sure at the C level that they're getting the exact results they require. Whether it be the signal to noise ratio in filters or the definition in videos, they can actually generate those images live using C simulation and check them before synthesis. Accelerated development is what Vivado HLS provides by synthesizing directly from C. Okay. The next thing Vivado HLS does is synthesis. Synthesis can easily be executed from the GUI toolbar, and we'll show an example of this shortly when we go through a small demo. Synthesis from C typically takes 10 minutes. Vivado HLS is never the bottleneck in any design process. You'll typically find that the slowdown comes when we get down to RTL synthesis. Before performing synthesis, we may want to add optimization directives. Vivado HLS makes this easy. If we open the Explorer pane shown there in point 1 and open the code in the main window, on the right-hand side, a directives pane will appear. All of the objects in this directives pane are objects in the C code which can be optimized. Simply by selecting the object and right-clicking, you can see the type of directives and optimizations that can be added to this object. And so by opening the C code, you can look through the C code, see the functions, see the arrays, see the loops, etc., which can be optimized. These directives can also be applied as tickle via using a tickle script, though Vivado HLS supports full batch mode. Okay. Another thing we can do with Vivado HLS is create multiple solutions. So if we look at the toolbar button there, there's an option to create a new solution based on the existing solution. If we look at the image there, you'll see there are actually 5 solutions being created, all from the same source code. Each one of them may just have slightly different directives and optimizations. They could be a different device, they could be different clock frequencies, or one could have optimizations added and the other not. The way Vivado makes it easier to look at these is it also allows you to compare solutions. So if you press the Compare Solution toolbar button, you get a view similar to that shown in the center of the screen, where we have 2 designs. Here we're showing Solution 1 and Solution 4 side by side. You can see that Solution 1 has a maximum latency of about 655 clock cycles. Solution 4 only takes 64 clock cycles. Okay. However, if we look further down at the area, you can see that Solution 1 only uses 3,500 LUTs, where Solution 4 uses nearly 12,000 LUTs. So you can see how the user can trade off area versus performance. Okay. Vivado HLS makes it very easy to run these trade-offs and view the differences. The other thing that Vivado HLS does is RTL simulation. The great advantage here is that the user does not have to create an RTL test bench. So long as the C file exists and can be simulated in C, Vivado HLS will take that C file and automatically create an RTL test bench based on the stimuli from the C input. When this is going to be simulated, as you can see, we can select any simulator. We can select XSim, iSim, ModelSim, Riviera. On Linux, we can also select VCS and NC Verilog as well. Or we could also just simulate using C and no HDL simulator. Okay. But again, this means that as soon as the design is synthesized, you can just press a button, select your simulator and press OK, and the RTL will be automatically verified based on the C input. Okay. The last thing we do when we're working with Vivado HLS design is create some IP. Okay. If we click on the last button, here you can see we can export it. This shows P-Core for EDK. It can also be exported to Sysgen, and more importantly, it can be exported to the Vivado IP catalog, and this is where we're seeing most of our designs go today. Okay. When this is done, you'll see that we create these subdirectories inside the solution, where you can just go pick up the IP and use it in the other Xilinx toolsets. Typically, this takes less than a minute to create. Okay. This shows an example of where we use the IP block. And we'll show this in a demonstration shortly. Okay. But you would basically just take this IP, include it in the Vivado IP catalog, and then it's available for use in the rest of the design. Okay. If you're going to use Vivado HLS, there is lots of help. From the welcome page, you'll see that you can open example projects. There are 20 design examples in there, and there are over 50 coding examples. These coding examples are taken from a 200-page coding style guide that's part of the user guide. So if you want to go in and see more details, help is there, and it's available right there on the product. In addition, online, there are a number of on-demand webinars. You can look at these. You can see how Vivado HLS can be used with a Zyng processor, and you can see how it's used in a system generator for DSP environment. These webinars were presented to customers, and they're recorded there online if you wish to view them. There are also a number of quick take videos created online for every aspect of Vivado HLS, from an overview through to verifying your design using IP catalog, system generator, platform studio, all the way through to using floating point design, how to use software libraries, and how to leverage the OpenCV design that we've been talking about in this presentation as well. Those are all available as online videos that you can watch at your own leisure. There are a number of application notes. Again, the aspects of from using processor control to using videos, floating point. Number of video application notes are out there. Feel free to download these, share them, read them, share them with your customers. And finally, there's the Vivado HLS documentation, which can also be reached from the welcome screen in the front of the GUI. For the tutorials, there are 10 tutorials for Vivado HLS. There's an introduction tutorial as an introduction to the tool. The tutorials on how to create a validate a C design, more details on how to perform interface synthesis, all the way down to using Vivado HLS IP in IP Integrator or with the Zyng processor design in IP Integrator and in System Generator for DSP. Finally, the Vivado HLS user guide itself, as you'll see, an overview of high-level synthesis. A coding style guide is included, as well as a detailed listing of all the commands. Finally, a number of articles are also available in the Excel magazine. Again, from using Vivado HLS and the Zyng to floating point designs to customer cases where customers are using it today, such as Agilent, or the latest one I think is from Nanyang University. Okay, all of this information can actually be reached from the Vivado HLS Resource Center. That's www.xilinx.com/HLS. Here you'll find links to all of these resources, giving you more information and more background on the things we've talked about today. Okay, so now that we've had an overview, it's time for a quick demo. Okay, so let's have a look at this, how we can use Vivado HLS and how we can use it within the rest of the Vivado tool suite. When Vivado HLS invokes, it invokes with a welcome screen. And so from here we can actually start to create our new project. If we click on create new project, the project wizard will open. Okay, so this is a matrix multiplier. So let's just call the project name matrix. And since this will be the directory on file, we'll give it the name _proj. And we'll give it the path to that directory. I'll just paste that in there. And then we'll go to next. Now this screen allows us to add the files for synthesis. Okay, so here we can add the files. And in this design, there's only a single file for synthesis, matrixmult.cpp. And here we add the top-level function name. Now remember, there can only be one top-level function for synthesis, and this is called matrixmul. Okay. We can now move to the next screen. And here we remove the files for the test bench. Again, we can add the files, and here we only have one file. It's called matrixmulttest. This is basically everything above the level for synthesis all the way up to the top-level function main. Okay. If we go to the next screen, you can see now we can actually select the configuration of the solution or our technology. We can change the clock period here, but we'll leave it at 10 for this example. And here we'll select the device. For this example, we'll select boards, and we'll go around and let's just select the CC702, okay? And so it automatically selects the device. And we can finish and open up the project. Okay, when the project opens up, we have our Explorer here on the right-hand side. So the first thing we can do here is we can actually simulate the C. I can go here, I get the C simulation dialog box. And the first thing I'll do is let's look at the debug, okay? Because that allows us to go through the debugger. So you'll see the design starts to compile. And when it finishes, we're going to change here from the synthesis perspective over to the debug perspective automatically. And that's done. Okay. And here we're inside a standard C debugger, so it's just the same as any other C debugger in the code. We could step into the code, we could step over the code, so we can just actually start stepping through the code. Now we see line by line, we can start to go through the code. Okay, or we can just run all the way to the end. And here you can see that this test passes, so we don't actually need to analyze this in detail. And we can go back to the synthesis perspective. Alternatively, we can see that the test passes there. We could actually just open the debugger and not run in debug mode. Just run a C simulation. It will run a bit faster. and it'll come up and we can see that the test actually passes. So we actually don't need to go into the debugger, but it's there, okay? And all the results from C simulation are stored in a directory called csim. The next thing we can do is actually run C synthesis, so let's run that. We'll just press the green button. Synthesis does not take long with high-level synthesis. As you see, it's already generating the RTL, it's finished. And when it's finished, the report will open in the main window. If we look at this report, we can come down and we can see our target was 10 nanoseconds. It looks like this design will finish in 8.6. The design takes 655 clock cycles to output a value. The interval is 656. So as soon as we're finished, we can start to put in new inputs. There's no pipelining. And if we come down, we can actually see the area estimates. So expressions are multiplications, additions, and any other operation at this level of hierarchy. Instances are sub-hierarchies. So in this example, you can see that all of the DSPs are in lower levels of hierarchy. There's nothing at the top level. And we can see the number of memories, etc. We can also come down to the bottom, or we could look at these in detail, but we can come down to the bottom and we can see the I/O ports that were added to the design. So here we can see the block level I/O ports that have been added to the design. A start signal, a done signal, an idle signal, a ready. Two of our inputs were arrays, so they've been converted into a RAM access, an A port, a B port, and a result port. All done with address, chip enable, write enable, and data. Okay. So the next thing we want to do is optimize this design. And to do that, first let's create a new solution. Okay. We just press the new solution toolbar, and we'll copy everything from solution 1 into the new solution, solution 2. Solution 2 is highlighted. To optimize things, we can open the source code. So before we do that, let's just clean up all the old windows. Okay, we'll close the C simulation windows. And we'll open the source code. When the source code opens, you'll see on the right-hand side, we now get the directives pane. Here are all the objects in this design we can optimize. So for this design, we're just going to select this loop and pipeline it. Okay, so let's just go in and select pipeline, and we'll press OK. And we'll go ahead and synthesize that. Okay, again, synthesis doesn't take long. And when synthesis completes, the report opens in the main window. And again, here we can see that by synthesizing this design, we've seriously improved the performance. We're now down to 71 clock cycles. We can see this a lot more easier by comparing the reports. So if I just compare solution 1 and solution 2, we can see that we've gone from over 500-600 cycles down to 71, 72. But you have see that our area has gone up. So we've nearly tripled the number of flip-flops and LUTs. But we have an almost 9-10x increase in performance. Okay. Now that we're happy with this design, the last two steps we can do are run RTL simulation. So here I could actually just select XSim. Let's do Verilog XSim simulation. I'll go ahead and press OK. And RTL simulation runs automatically. Now, as we saw in the C simulation, the C test bench actually had some code that checked the results. If we open the C test bench, we can come down here, and you can see that actually does a check to see if there's a mismatch in the data. Now that we have RTL taking the place of our C function, that same checking can now be performed. This is the big advantage here, is that we can now just run RTL simulation and it will come back and tell us if the RTL matches the C simulation automatically. No work needs done by the user. And we'll just give that some time to run. And there we go. So we're now guaranteed that the RTL is the same as the C, provided the C simulation exercised the design thoroughly. Now that we're happy with this design, we can package it up as IP. So if we select IP, we can select the Vivado IP catalog. If we wanted, we could actually give it some names and some version numbers and give it some descriptive values, etc. But for this case, we're just going to export it. If we come down to solution 2, here we can see the working directories of simulation and synthesis. When the IP packaging is complete, we'll see another directory here for the implementation. And these are our final results that we can actually take and use. outside of Vivado HLS. So when the IP generation is complete, here we see an implementation directory. If we just expand this, we'll see that there's a directory called IP, Verilog, and VHDL. We just expand this window a second. Within the IP directory, here we'll see our IP package. And we'll use this in just a moment. Down here we have our final Verilog and VHDL directories. For example, if we expand this, here we can see all the files. And also what you'll see here is a Vivado project. If we double click in this, we can actually open things up inside Vivado. To show you how this will be used, let's go look at a Vivado project. Okay, so let's switch screens to Vivado for just a moment and import this IP. So here we have a Vivado project. Okay, so let's open up the IP catalog. We first need to add that IP to our design. If we come in, IP settings, let's add some IP to our repository. We've already created a repository here. The repository is called repo. We go into the matrix multiplier design, the matrix multiplier project. We're solution 2, implementation, IP, and there's our IP package. We can simply just now add this into our package. We can see it's here. Okay, but if we close this, now inside our IP catalog, if we expand Vivado HLS, we can see that there now is a matrix multiplier piece of IP. If we go and create a block diagram, let's call it design 1. Here we could actually just add IP, I believe, type HLS won't work, matrix mate. There's our matrix multiply block. And we just instantiate it in our IP design. Okay, that shows how that's used. If we go back to Vivado HLS, alternatively, if we go into the Verilog or VHDL directories, let's just choose VHDL. We could click on the Vivado project, and it will take this design, instantiate it in a Vivado project for us with the RTL test bench that we just generated using RTL Sim, and provide that for analysis. And here we have our design inside in a Vivado project where we can start to do detailed analysis if we prefer working at the RT level on this. Okay. So that shows you how we can import things into the rest of the Vivado design suite. And that completes this demo. So thank you everyone. We'll look forward to seeing you at TSC this year and seeing you successfully use Vivado HLS.